So last time around, we started off a new topic on the course, which is reasoning about programs. And we did a couple of things last time around. We looked at what actually is equational reasoning, and then we started to think about how you can apply this idea to reasoning about Haskell programs. So what we're going to be doing today is we're going to be looking at the principle of induction on two particular recursive data types, a data type of numbers and a data type of lists. And for most of you taking this course, this should be a revision. Most of you should have seen induction in some form or another before, probably many times before. But my experience of teaching this kind of stuff for many years is that many students still struggle with the idea of induction, even if they have seen it many times before. So what I'm going to be doing is introducing you to the principle, and the emphasis I'm going to place is on how you actually do the proofs. So we're going to kick things off by looking at induction on the natural numbers. So I'm going to define or declare a simple data type of natural numbers. So we're going to say we have a new data type called nat for natural numbers, and it's going to have the obvious two constructors. We're going to have 0, which represents 0, and we're going to have a successor constructor which represents the idea of incrementing a natural number. So this declaration then, as usual, defines or declares three things. We're declaring a new type nat, and a constructor 0 that doesn't take any parameters, and a constructor called successor, which takes a single natural number as its parameter. So in terms of the values which are defined by this data type, we have an infinite sequence of values. So in particular, we have the value 0. That's just the basic constructor. Then once we have any old value, we can apply the successor constructor to it, and we can generate a new natural number. So we have successor 0 as well. And then of course we can apply successor to that and get successor of 0, and so on. Okay, so we can apply the successor constructor as many times as we like, starting from 0 to build up arbitrary large numbers. And obviously these just represent the normal natural numbers. Here we have actually a representation of 0, 1, 2, 3, and so on. So an important point to emphasize here is that these kind of expressions we're constructing here, these are just data. They don't have any inherent meaning to the Haskell system. They mean something to us. When we look at successor of 0, we can think, oh, that's probably going to represent the number 2. But to the system, they have no inherent meaning. They are just data. One other small technical point to just note before we move on, there is also an infinite value in this data type. We can actually define infinity. Infinity is a natural number, so it's a nat, and we could simply say that infinity is the successor of infinity. So if you were to unwind or run this definition, it would just print an infinite sequence of successors. So this is a perfectly well-defined value in a lazy language like Haskell, but we're actually not going to be considering this value when we think about induction. So we'll forget about infinity, and we're just going to consider the finite natural numbers, which you can build by starting from 0 and applying the successor constructor a finite number of times. So now that we've defined the data type of natural numbers, we can formulate the principle of induction. This is very straightforward. It's an inference rule, so I can draw a little horizontal line first of all for my inference rule. And the name of the game with induction is it gives you a method of proving that some property P is true for any natural number, or rather for every natural number. So we can write that down formally. We can write for all n that the property P is true for n. And what induction gives you is a way of breaking this problem down. It says you need to prove two things in order to prove that some property is true for every single natural number. And the two things you need to prove are very simple. First of all, you need to prove a base case. You need to prove that the property is true for 0. And then you need to prove an inductive case which says that the property is preserved by the successor constructor. So that sounds a bit fancy, but if we actually write it down formally, it's very straightforward. This simply means that for any natural number n, if the property p is true for the number n, then it's also going to be true for the successor of n, the next natural number. Okay, so again, this one is called the base case, and this one is called the inductive case, and the inductive case says if the property is true for any number n, then it's also going to be true for the next number. And together, these two properties are sufficient to ensure that the property holds for any natural number n. So you can ask yourself, why is this principle actually valid? So for example, if I've proved the base case and I've proved the inductive case, how do I know that it's actually valid for a number like 4? So we could work this out. So let me write down the first few natural numbers. So if I had 0, if I had successor of 0, and I had successor of 0. Actually, let's not go up to 4. Let's just leave it as 3. Can't fit it on the slide here. So there's the first 4 natural numbers, 0, 1, 2, 3, 4. Suppose now that I have proved the base case, that it's true for 0, for some property p, and I've proved that the property is preserved by the successor constructor. So if it's true for n, then it's true for successor of n. If I've proven these two things, how do I then know, what's the intuition about why it's true for any old natural number? And the idea is very simple. If you've proved it's true for 0, then let's tick this one off down here. If I proved it's true for 0, I know my property is true here. And then by the inductive case, if I've proved that if it's true for n, it's true for successor of n, I could take n to be 0, and then I can tick off successor of 0, and then you see the pattern now. Once you've ticked off any number, you've proved the property of it, then you can tick off the next one, and the next one, and so on. And so what this is giving you is a little procedure really for proving that the property is true for any number just by successively starting from this, base case here and applying the inductive case here. So that's kind of one way to understand what's going on with the induction principle. Let me give you another kind of pictorial way of understanding what's going on as well. So imagine you have some dominoes and you line them up on a table, and you line them up so that they're close enough together that every domino will topple its neighbor. And what induction is really giving you then is it's explaining how you can topple as many dominoes as you like. Okay, so what induction says is if you can topple the first domino and each domino can topple its neighbor, then you can topple any number of dominoes that you like. Okay, so just to kind of illustrate this again, if I could topple this one over, I just push it over, and I've arranged it so that it's near enough to its neighbor that that one will topple, and then that one will topple, and so on and so on. And in this manner, you can topple any number of dominoes. So this is the principle of induction for the natural numbers. So what we're going to do now is give an example of applying the principle of induction in practice. So what I'm going to do is I'm going to give you a simple recursive definition for a function which adds together two natural numbers. So we take one number, we take another number, and we add them together to give a natural number result. And this has a very simple two-line definition. If you add 0 onto any old natural number m, then you simply give back m. And if you add the successor of any natural number n onto any other natural number m, then the trick is all you're going to do is do successor of add n m. Okay, so nice, simple, two-line recursive definition. And what we're going to show is a simple equational property of this function. And the property we're going to show is that if you add any old natural number n and 0, then you're going to get the same number n back. So if you look at the recursive definition for the function, in the base case, we see that if you add 0 on the left to any natural number, it doesn't change the number. And what we're going to show now is the corresponding case for the right. So if you add 0 on the right of any old natural number, then it doesn't change the number. So in order to prove this by induction, we're trying to do this kind of precisely here. So let's first of all define the property which we're trying to prove. So we're trying to prove that the property P is true for any old natural number n, or for every natural number n, and the property is defined to simply be if you add n and 0, then you're going to get the same number n. So let me put this in a little red box here. So this is the property now that we want to be proving by induction. We want to prove that for every natural number n, the property P of n is true, where P of n is this property here. So we're going to be proving this property by induction. So we need to show two things. We need to show the base case, and we need to show the recursive case or inductive case. So let's do the base case first of all. So what we need to show is that the property P holds for 0. So what does this actually mean? Well, we can just go to our property. So the property P of n is add n0 equals n. So if n happens to be 0, then all we need to show on the right hand side is that add of 0 and 0 is 0. Okay, so we can go back over here and we can be precise about what we're trying to do. We need to show that add of 0 and 0 is 0. Okay, so let me just put this in a little red box to indicate that this is what we need to show. And of course, this is completely trivial to show this, but let me actually do the little equational reasoning calculation. So what we need to show is that add of 0 and 0 equals 0. And why is that the case? Well, by definition, add of 0 and anything is the anything, and in this case the anything is 0. So if I simply applying the definition of add, so I'm typically going to write some hints between my steps to explain what I'm doing. So if I apply the definition of add here, then I get down to 0. So I've shown exactly what I needed to show now. I needed to show that add 0, 0 is 0, and I've just shown that in one trivial little step by applying the definition. So then we can move on to the inductive case, and this one is a little bit more sophisticated. So what do we need to show? So in the inductive case, what we need to show is that if the property P is true for any number n, then it's also true for the next number, successor of n. So what does this actually mean? So let's spell this out again. So P of n means precisely that add of n and 0 is n. That's exactly what P of n means. So just expanding out P of n is exactly this. So then I can expand out P of successor of n, and that simply means, so write down the implies, that simply means if you add the successor of n to 0, then you're going to get successor of n. And again, I can put this in a red box to emphasize that this is the thing which I now need to prove. And then you might look at something like this and think, well, this is quite a complicated stuff. It's one full line. How do I go about proving something like this? Well, the strategy here is you typically start with the largest sub-expression, which in this case is add of successor of n to 0. And you're going to try and prove it's equal to the other part here. And along the way, you can assume this because you have an implication here. So this part here is called, as usual, your induction hypothesis. Okay, so let's start with that largest subterm. So we have add of successor of n, and then 0, and we want to show that that's equal to successor of n, and we'll just do some simple equational reasoning steps. So let me make a little bit more space here. So what can we do? Well, we're adding the successor of something on to something else, so we can use the definition for addition. So if we simply apply the definition for addition at this point, so applying add, what we will get back is successor of add n and 0. Okay, and then we can stare at this and think, well, what could we do with this? Well, actually, if you look inside the brackets, so if you look in here, this is exactly of the form of the induction hypothesis. So by induction, we're allowed to assume that add n0 is the same thing as n. Okay, so we can apply our induction hypothesis now, and we can replace that term in the brackets by induction. So by the induction hypothesis, then we're going to get successor of n. And now we're done, because what we needed to show is we need to show that this equals this, which is exactly what we have done. And along the way, we're allowed to assume inductively that add n of 0 is n, and that's exactly what we used down here. So this completes the proof by induction that this property P is true for any natural number n. So this is our first example of an inductive proof over the natural numbers. So for our next example, we're going to do something slightly more sophisticated. What we're going to do is prove that the addition operator is associative. So what does this actually mean in terms of an equation? Well, it's very simple to write down. We simply say, if you add x and you add y, z, so here we're adding three numbers x, y, and z, but bracketed towards the right. That should be the same thing as adding them, but bracketing towards the left. So if I do this addition, or these two additions, this should be the same as the left-hand side. So all this is saying is if you add three numbers, x, y, and z, it doesn't matter the order in which you add them. So we're going to do an inductive proof over natural numbers, but we've got three parameters to consider. We've got x, y, and z, which are all natural numbers. So which one of these three parameters are we actually going to do the induction over? And what can help you here is thinking about the manner in which the addition function itself is actually defined. So addition is defined by recursion on its first parameter. We match the first parameter to either be 0 or the successor of something. So what we can do here is look to see where do x, y, and z actually occur as the first parameter to an addition operator. So if we look at x first of all, here is the x on the left-hand side. It's the first parameter to the first add, and on the right-hand side, it's the first parameter to the second add. So x appears in the recursive position that for the way in which add is defined twice. If we look at y, on the left-hand side, it's in the first position on the second add, and it's in the second position on the second add here, so we won't count that one. So y appears in the recursion position once. And if you look at z, it's in the second parameter place on both sides, so we don't count this at all. So the summary here is that in terms of the parameters x, y, and z, x appears in the recursion position twice, y appears once, and z appears in this position not at all. So the kind of suggestion here is that we should try, first of all, doing recursion on x, because it appears, or induction on x, because it appears in the recursive position the most number of times. So before we move on to actually doing the proof, let's be precise about the property which we're defining. So we're going to define the property P for any or for every natural number x, because that's what we're going to be doing induction over, and we're going to say that you simply add x to add y and z should be the same thing as add of x, y, and z. Okay, so again, let me put this in the little red box. This is the thing that we need to prove now for every natural number x. If you're eagle-eyed, you might think, well, what is the nature of the variables y and z in the right-hand side here? Because I haven't put any quantification. X is bound on the left-hand side, but y and z are just kind of free variables at this point. So if I wanted to be super precise, what I would actually need to do is in here put some quantifiers. So what I would need to do is write for all y and for all z, then that thing in the red box must be true. But I'm going to be a little bit loose here. I'm not going to explicitly write these quantifiers in, but they are actually there. And if you needed to, or if you wanted to prove something like this in some kind of mechanical proof assistant, then you would actually need to be very explicit about these quantifiers. But for now, I'm just going to know that they are actually there. So this is the name of the game now. We need to prove that this property P is true for every natural number x. So as usual, we will do the base case first, which involves proving that the property P is true when the natural number x is 0. So what does this actually mean? Well, all we need to do is look to our definition for the property P. So P of x is all of this. So when x is 0, we just copy down the right-hand side, but replacing x by 0. So this is very easy to do. So i.e., if we spell the property out, we need to show that when you add 0 onto add of y and z, that is the same thing as adding of 0 and y onto z. Okay, so again, let's put this in a little red box, because this is what we're trying to prove, or what we need to prove. So what do? Well, we need to start with one of the two sides. So typically you think, well, what's the most complicated thing? Well, in this case, both sides are kind of equally complicated, so it doesn't actually matter much which one we start with. So let's just start with the left-hand side. So what we're going to do is have add of 0 of add of yz, and then see what happens. Well, the first step is very simple. Here we're adding 0 to something, and by definition of the add function, if we add 0 onto anything, then we just get the anything. So here, if I'm applying the definition of the add function, I will simply get add of yz. And then we can think, well, what do I do now? Well, at this point, I can't simplify anymore because I've already got the simplest possible thing I could have. I've simply got add of y and z. And I don't know anything about y and z, so I can't apply any definitions. So we're a bit stuck at this point. And at this point, one of the strategies which you can apply is working backwards. So at this point, we have been working downwards. What we could do now is actually think about working backwards. So what I'm going to do is actually go down and think, well, what are we trying to reach? We're trying to reach this expression here. So we have add of 0 and y, and then z. So that's what we're trying to reach. We're trying to reach this expression here, which I've simply copied down here. And now I can think about working up the way. What could I do with this expression? Well, if I look at this expression, inside the brackets here, I have something which I can simplify. If I add 0 onto any natural number y, by definition of the add function, that is simply going to be y. So if I was going up the way, so let's put a little arrow in here. If I was going up the way, it would be very easy to know what to do, just as when I came down the way here, it was very easy to know what to do. So if I wanted to move from here to here, I would simply be applying the definition of the add function to simplify this part inside the brackets. So if I wanted to go the other way from here to here, I could unapply the definition for add. So the trick here is if I just write in here unapplying add, then that will be the correct answer in the end. So this idea of kind of working downwards until you get stuck and then working backwards and trying to meet in the middle, this is a very common strategy when you're doing these kind of equational reasonings. We'll see quite a few examples of this kind of strategy in the course. So to complete the proof, we need to do the inductive case now. So what we need to show is we need to show that if the property P is true for any natural number x, then it's also true for the successor of x. So as usual, we can spell out what this actually means. And this time around, we need to write quite a lot of stuff down to do this. So I need to make sure I leave enough space. So P of x is simply the associativity property for x. So if we have add of x and add of yz equaling add of x, y, and z. So what I've just written down here, all of that is P of x. And then we have an implication, and that had better be the same, or that should entail, add of successor of x. So the same property, but with successor of x written instead of x. And that should be add of successor of x, and then y, and then z. Okay, so all of this stuff here is simply P of successor of x. And as usual, I'll put what we're trying to prove into a little red box. So there's an awful lot of stuff inside this box, so we need to think carefully about what is our strategy for actually proving this. And actually, it'll be the same strategy we've seen already. We're going to take the most complicated thing, or one bit of the most complicated thing. So we're going to start with here, and we're going to try and prove that it's equal to this thing here. And along the way, we can assume this equality, which is our induction hypothesis. So it's the same strategy that we've seen before. So let's start with this part here in yellow and see what happens. So we've got add of successor of x, and then add y, z. And this time around, I've not really got enough space to write in the hints, so I'm not going to do that this time, but I'll tell you what the hints are. So what are we going to do this time around? Well, we've got add of successor of something, so we can simply apply the definition of addition. Okay, so if we apply the definition for addition, what we're going to get in this case is successor of add x and then add y and z. So I've just applied the definition to move the successor constructor to the outer point. So then we can look at this expression and think, well, is there anything we can do with it? And yes, there is, because inside the brackets, we have add of x, y, z bracketed to the right, which is exactly what we have up here. So by induction, we're allowed to assume that that's the same thing as bracketing the other way around. So I could apply my induction hypothesis at this point inside the brackets there, and what I would get is the same thing, but re-bracketed the other way around. So I get add x, y, and then z. So now I can look at this expression and think, well, is there anything which I can do with this? Well, I can't apply the definition of add because I don't have a successor or a zero constructor in the right place. And I don't know anything further about x, y, and z, so I seem to be a bit stuck. So if we think about what we just did, when we got stuck, we were working forward, and then we ended up working backwards as well, and trying to meet in the middle. So we can apply the same trick here. We're stuck at this point, so let's try working backwards instead. So let me write down a couple more equalities down here. What we're actually going to have in the end is we're aiming to get down to add of successor of x and y and z. And what I've written down here is simply this thing here. So this is what we're aiming for, and we're now going to think about working up the way rather than down the way. So we worked down to here, and then we got stuck. We didn't know what to do. Let's try and work backwards now and try and meet ourselves in the middle, and hopefully that will complete the proof. So let's have a look at what we've got down here. Is there anything which we could do with this? Well, this time we can do something. We can simplify, because inside the brackets here, we're applying an addition to the successor of something. So we can simply apply the definition of addition. So if we apply the definition of addition to move up here, what we would get is add of successor of add x, y, and then z. So all I've done is I've expanded the definition for addition here, and I've got this part here. Okay, and then we can think, well, what can we do now? Is there anything we could do to simplify this part? Well, again, the answer is yes. What we have here is the addition of the successor of something to something else. And if we simply apply the definition of addition once more, what we will get is this term here, and we've actually met ourselves in the middle. Okay, so now we have completed the proof. And I fully appreciate that looking at someone doing these kind of proofs is not much of a spectator sport, but you do need to learn how to do these kind of proofs for yourself. I mean, we've seen two simple examples now of proofs on the natural numbers, and we did a simple one first, and then we've done a more sophisticated one now with the associativity of addition. So not much of a spectator sport, but make sure you can do these kind of proofs yourself and that you know the tricks of the trade about how you actually proceed. For example, try working forward, and then when you get stuck, try working backwards. So what we've seen now is the induction principle for natural numbers and a couple of examples of how to use this in practice. But we're computer scientists, we're more interested in other data structures than numbers. So let's see now how we can apply the same idea and have an induction principle for lists in the language like Haskell. So we're going to think first of all, how do you actually formulate the induction principle? So it's going to be an inference rule as before. So I can write a little horizontal line here. And this time around, we're going to say for all lists x's that some property p is true for the list. Okay, so the name of the game is given any old property p of lists, we want to prove that it's true for every possible list. And what the induction principle allows us to do is to break this down in the standard way. So we're going to have a base case which says that you must prove that the property is true for the empty list, so that's the list with nothing in it. And then the inductive case says the property is preserved by adding one extra element onto the list using the colon operator. So again, how do we write this down formally? So we say for any element x and for any list x's, it should be the case that when the property is true for the list x's, then when you put one additional value x on the start of the list using the colon operator, then the property is still true. Okay, so again, just to read this in English one more time, the conclusion says, if you want to prove that some property p is true for any old list x's, then the preconditions say that you prove the base case, which means that the property is true for the empty list, and then you prove the inductive case, which says if it's true for any old list x's, then it's also true if you put one additional value on the start using the colon operator. And just one little side kind of technical note, you need to assume the obvious typing assumptions in here. I mean, I haven't written down anything about types, but there's implicit typing constraints on the variables x and x's here. So that's the principle of induction for lists. What could we actually do with it? So let's consider a simple example. And the example I want to consider is, suppose we define the familiar reverse function. And I'm going to be writing reverse quite a few times here, so let me abbreviate it by rev, but it's the same function that you're familiar with. So rev takes a list of things and gives you back a list of things, and the base case is if we reverse the empty list, we get the empty list, and if we reverse a non-empty list, all we're going to do is reverse the tail of the list and then put the first thing on the end, sitting on a little list on its own. So standard recursive definition for the reverse function, what could we show? So this time around, what we're going to show is that if you reverse a list twice, then you get back where you started. Okay, so this is the property we want to show. For any old list x's, if you reverse it once and then reverse the result, you will get back where you started, and we want to show it by using mathematical induction, or rather structural induction, over lists using this definition for the reverse function. So this time around, the base case is actually extremely simple. All we need to show is that if you reverse the empty list twice, then you get back where you started. So here is reversing the empty list and then feeding the output into the empty list. And this time around, it's so simple, I'm not actually going to write the hints down at all. If I reverse the empty list inside the brackets here, that's completely trivial. I'm going to get back the empty list. So I can replace the brackets by the empty list. And then I simply do exactly the same again. If I reverse the empty list, then I get down to the empty list. Okay, so completely trivial base case. In the inductive case, let me first of all write down what it is I need to prove. So what I need to prove is that if I reverse of x's equals x's, then if I do the same thing but with a list with one more thing on it, I'll get a list with one more thing on it. Okay, so this is the property I need to prove. That's my inductive case. And I just follow the normal kind of advice or rules of the game at this point. I start with the most complicated thing, which is this. I'm going to try and show that it's equal to this. And along the way, I'm allowed to use my induction hypothesis. Okay, so let's see what happens this time around. So I'll start with the most complicated thing, which was reverse of x colon x's. And then I'll think, what do I need to do? So I don't actually have enough space on the screen here to write the hints, so I'll just explain the hints. So the first step is very obvious. I know how to reverse a non-empty list. I reverse the tail and then put the first thing on the end. So what I can do here is simply get the right pen. I can reverse, and then inside the brackets, I'm going to get reverse of x's, and then I put x on the end. And now I can think, well, what am I going to do with this? Okay, so I don't actually know what to do at this point because I can't apply the definition of reverse, and yeah, I can't apply my induction hypothesis, so I'm a bit stuck. So at this point, you might think, well, I'll use the other piece of advice, which is to go to the end and kind of work backwards. But if I write x colon x's at the bottom of the slide here and then try and work backwards, x colon x's is already in its simplest form, so it's not clear to me what I could do at this point. So I'm kind of doubly stuck. It turns out that the right way to get out of being stuck this time around is to actually use a little auxiliary result about reverse, which is how it distributes over append. Because you see, what you have here is you're reversing the append of two lists. So let me give you a simple property, or as we call it in mathematics, a lemma about reverse. And here is the simple distributivity lemma. So distributivity, make sure I get the spelling right. Here is a distributivity lemma. It simply says, if you reverse the append of two lists x and y, then it's the same thing as reversing the second list plus reverse of the first list. And it's kind of intuitively obvious why this is correct. I mean, if I take a list like 1, 2, 3 and I append it to 4, 5, 6, I'm going to get 1, 2, 3, 4, 5, 6. And then if I reverse that, I'm going to get 6 down to 1. And what you see on the right hand side is that's the same as reversing the 4, 5, 6 to get 6, 5, 4, reversing the 1, 2, 3 to get 3, 2, 1, and then you append these and you get the same thing. So what you see here is that the reverse function is distributing over the append function, but you need to remember to swap the order of the arguments. So here I have x's and y's, and on the right hand side I have y's and x's. So this is a useful little distributivity lemma. So I could use this here because what I have inside the brackets, or in this line here, is I've got reverse of something appended with something else. So I could use my little distributivity result here, and what I'll get then is reverse of the second thing, which is the x, plus reverse of x's. So I've simply used my little distributivity property here. So then I can think, well, what can I do now? Well, let me look at this part here. And actually, it's kind of trivially obvious that if you reverse a list with one thing in it, you are going to get the same list. But this is actually another little lemma which I could have. I could have a lemma, let me call it the singleton list lemma. Singleton lists lemma. And what this result would say is if you reverse a list with one thing in it, then you'll get back simply the same list with one thing in it. Okay, and we'll come back to these lemmas in a second. So what could I do with this? Well, I could apply this little result to this sub-expression here, and I could say that's the same thing as x, and then I have copy everything else down, reverse of x's. And now I can think, well, what am I actually going to do at this point? Well, I could focus now on this sub-expression, and I see this is exactly what I have in my induction hypothesis. So by induction, I'm allowed to assume that if I reverse of x's, then it's the same thing as x's. So I could apply my induction hypothesis to this part here in yellow, and that would simply be then copy that bit down, and this is simply x's. And now I'm basically done. All I need to do then is apply the definition of plus plus. If I append a list with one single element on it, if you unwind the definition of the plus plus function a couple of steps, what you'll find is you get exactly what you need, which is x colon x's. So what you can see here now is we've started with this, which is this term here, and we've shown it's equal to this, which is this, and along the way we used the induction hypothesis, which is this. Okay, and as we saw, along the way also we needed to have these two lemmas. One simple distributivity lemma, which explains how reverse distributes over append, and one singleton list lemma, which explains that if you reverse a list with one thing in it, then you will get a list with one thing in it. And finding these kind of lemmas is quite an art. This is where you need a bit of experience sometimes when you're doing these kind of equational reasoning proofs. So a couple of little exercises here for you. You could try and prove these two lemmas using induction. And what you'll find is that the proof of the first one, the distributivity one, it actually requires another lemma, that the append operator, which is used twice, it's used here and here, that the append operator is actually associative. So proving these two distributivity lemmas and then proving the associativity of append, these will be very nice additional exercises for getting familiar with doing induction on lists. So that's it for today for our kind of refresher and kind of introduction to induction. And we've seen how to do it on natural numbers, which probably is familiar to you. And we've seen how to do it on lists, which is maybe new. So what we're going to be looking at next time is we're actually going to be looking to see how you can make the append operator, like this one here, vanish from your programs. So that's it for today. I will see you again next time around.